Hello my friends and welcome back to the Today Machine channel. Design Department and Laminations. The production begins in the design department, where engineers conceptualize and develop detailed plans tailored to the machine's specifications. Advanced software tools are utilized to create precise designs that meet performance requirements. Laminations, which form the core of the generators and motors, are prepared with precision. These thin sheets of electrical steel are processed to reduce energy losses and improve efficiency. Welding and tool making. The welding stage involves assembling key components with high precision to ensure structural integrity and mechanical stability. Automated and manual welding techniques are applied depending on the component's complexity. Simultaneously, tool-making operations produce custom tools required for subsequent production processes. High-precision tools are crafted to support machining and assembly tasks, ensuring consistency across units. Ringent, with parts being inspected against predefined tolerances to guarantee flawless assembly. Machining is a critical phase where parts are shaped and finished to meet exact specifications. This includes the production of shafts, casings, and rotors using CNC machines and other advanced equipment. Each machined part undergoes rigorous checkups to ensure dimensional accuracy and surface finish. Quality control is the production of TES generators and motors follows a designed and streamlined process to ensure optimal quality and performance. This process encompasses several critical stages, each contributing to the final functionality and reliability of the machines. Test field and paintwork. Once assembled, the machines are transferred to the test field for performance validation. Testing includes load tests, insulation resistance tests, and thermal performance evaluations to ensure each generator or motor meets operational standards. After passing all tests, the machines are prepared for the final stage, paintwork. A robust coating is applied to protect the machine from environmental factors like moisture, corrosion, and UV radiation. Dispatch and applications. The finished products are packed securely and dispatched to their respective destinations. TES generators and motors find applications in diverse sectors, including small hydroelectric power plants. For example, installations such as the Bulary Hydro Power Plant in the Czech Republic utilize TES machines for efficient power generation. This facility employs two GSH-400 synchronous generators, each rated at 397 kVA with a speed of 750 revolutions per minute, and two GSH-1120 synchronous generators rated at 2400 kVA with a speed of 187.5 revolutions per minute. Winding and assembly. The winding process is fundamental for electric machine performance. Copper windings are carefully installed on the stator and rotor to optimize electromagnetic efficiency. Skilled technicians ensure precision during this stage to prevent defects. After winding, the components are assembled into the final machine configuration. Assembly includes integrating bearings, rotors, stators, and other critical parts into a cohesive unit. Additionally, A GSH 800 synchronous generator with a rating of 1100 kVA and 250 revolutions per minute is deployed for optimized performance. The high-voltage electric motor rewinding process involves several steps to restore motor performance. It begins with cleaning, steaming, and drying the motor, followed by sandblasting. Technical drawings for machining operations are prepared by an in-house engineering team. The rewinding process is then performed on components like the stator, rotor, and electrical brakes. Additional steps may include machining parts such as bearing housings, rotors, and motor feet. If needed, welding of rotors, stators, frames, and shaft blocks is done, along with balancing rotating parts. After assembly, coating is applied, and the motor undergoes extensive testing. A final report with performance measurements and recommendations for maintenance is provided. The production process at Agrawal Metalworks involves several coordinated steps to transform raw materials into high-quality copper and copper alloy products. The process begins with casting, where copper, brass, and phosphorus bronze alloys are produced using both direct chill vertical casting lines and horizontal continuous casting lines. These systems, sourced from renowned suppliers, ensure the production of high-purity metals with precise control over the alloy composition. Once the casting is complete, the material undergoes hot rolling to remove any oxide layers, preparing it for further processing. This step involves passing the metal through rollers to achieve the desired thickness and surface finish. The hot-rolled coils are then subjected to a cold rolling process, where ultra-high response automatic gauge control systems are used to ensure tight tolerances on thickness and shape. The cold rolling mills, including the Waterbury Farrell 4 high mill and the quad mill, are designed specifically for rolling copper and brass foils as thin as 30 microns, ensuring uniformity and precision. In addition to thickness control, the cold rolling process also influences the material's hardness, elongation, and grain structure. Bell furnaces are employed to control temperature during this stage, with digital and microprocessor-based systems that allow for uniform grain structure and desired mechanical properties. The metal is then stretched and leveled using a precision stretch leveler, ensuring flatness and high-quality surface finish. This process is crucial for achieving the required quality, particularly for applications like stamping and welding. The final step in the production process is slitting, where the cold-rolled strips are cut to precise widths. This operation is carried out with high-speed slitting machines to maintain consistency and accuracy. After slitting, the products are packed according to customer specifications. The packing process is carried out using advanced machinery to ensure protection during storage and transit, with moisture control measures in place to prevent corrosion. Throughout the entire production process, strict quality control measures are in place, ensuring that any material not meeting the required standards is promptly rejected. Advanced testing equipment, including spectrometers and tensile testing machines, is used to verify the physical and chemical properties of the products, ensuring consistency and high quality across all production stages. The production process of square cans involves several key steps. First, high-quality sheets of metal, typically tin plate or aluminum, are cut into precise shapes. These sheets are then lithographed for branding and coated to ensure corrosion resistance. Next, The body of the can is formed by shaping the metal sheets into a square profile and sealing the edges, often using advanced welding techniques. The square can production industry is a significant segment of the global packaging sector, valued at an estimated $20 to $25 billion. These cans are widely used in the food, chemical, and industrial sectors due to their durability, recyclability, and space-efficient design. In 2023, global production exceeded 10 billion units, driven by growing demand in regions like Asia-Pacific and North America. The bottom and top ends are added through a process called double seaming, ensuring an airtight and leak-proof finish. Additional features, such as handles or spouts, are incorporated based on the intended use. Automation and precision engineering have streamlined the manufacturing process, reducing waste and increasing efficiency. With a focus on sustainable practices and innovative designs, square can production continues to evolve, meeting diverse market demands effectively. China's synchronous alternating current (AC) generator production industry has experienced substantial growth, underpinned by advancements in manufacturing and an expanding energy infrastructure. The industry's output has risen significantly over the years, demonstrating China's dominance in the global market. In 2005, China produced electric generators with a total capacity of 92 gigawatts (GW), showcasing its early prominence in the sector, Statista. These regional figures highlight a thriving and competitive industry, with varying outputs depending on local capacities and energy demands. Large-scale projects further illustrate China's capabilities. The Three Gorges Dam, a globally renowned hydroelectric facility, houses main generators each capable of producing over 700 megawatts (MW) of power. These massive synchronous AC generators reflect China's technical expertise and ability to meet high output demands. Wikipedia. National standards, such as GB T 7409, play a crucial role in maintaining the quality and consistency of synchronous AC generator production. The Hermli C60 is a dynamic 5-axis mill-turn machining center designed for high-precision, efficient processing of both CNC milled and turned parts. With a focus on energy industry applications, such as machining fan disc components from 1.2738 steel, this center offers exceptional performance for complex parts up to 2,500 kg. The C62, as the flagship of the Hermli high-performance line, combines advanced features for optimized machining. These include sophisticated fluid technology, an efficient chip management system, and versatile cooling lubricant units. The system also offers several workpiece loading options for seamless operations. The high-performance center is equipped with a hinged belt conveyor for effective chip disposal and can be transported and set up without the need for foundation work. Built for energy efficiency, the machine incorporates lightweight construction, mineral casting, energy recuperation, and high-quality servo drives, ensuring low operating costs and long service life. The Coro Mill 170 is a high-precision rough gear milling tool designed for modules up to 12 dp 2.117. It operates with a cutting speed, VC, of 200 meters per minute, 655 SFM, and a feed rate, VF, of 1090 mm per minute, 42.9 inch per minute. With a robust P2 material body, it ensures efficient and accurate gear production. The production process for the ITCT 771 power amplifier involves several key stages. Initially, semi-finished product plugs are prepared and undergo wave soldering to ensure proper connections. Once soldering is complete, the semi-finished products go through a debugging process to verify their functionality. Following debugging, the products move on to final assembly, where all components are carefully put together to form the complete amplifier. After assembly, the products undergo a series of rigorous quality checks, beginning with a thorough quality control (QC) inspection to detect any defects. If the products pass QC inspection, they proceed to additional debugging to fine-tune their performance. To ensure long-term reliability, the products are subjected to an aging test, which simulates extended use under varying conditions. Subsequently, they undergo a final product quality control (PQC) test to confirm their operational standards are met. The final step in the process is the packing stage, where the finished products are securely packed and prepared for distribution. Steel wire rope lifting systems for cargo baskets and cutting skips are designed to meet specific client requirements. Each system features four 22 mm galvanized wire rope legs with omega shackles at the ends, connecting to the baskets or skips. A central 32 mm galvanized wire rope leg attaches securely to the crane hook. These systems are engineered to safely lift loads up to 12 tons within a working angle of 0 to 30 degrees. The robust design ensures stability and reliability, making them ideal for heavy-duty lifting operations in industrial settings. The Axpo project Linthal in Switzerland involved the installation of a 380 kV underground cable system designed to integrate the new 1 GW pump storage plant located between Tierfed and Limmer. Preliminary studies and model development. Many years ago, preliminary studies were conducted to evaluate the feasibility of the installation under the project's challenging conditions. This included constructing a 1:1 scale model of the joint bay to simulate and validate the installation processes. Key challenges such as the steep 24% slope of the 1.2 meter wide tunnel required innovative solutions to facilitate safe and efficient cable laying. This ambitious engineering project was characterized by planning, advanced technological solutions, and rigorous testing to ensure efficiency and reliability. Cable production and testing. The core of the project was the 380 kV XLPE insulated cables with copper conductors. Each cable measured 645 meters in length and weighed approximately 27 kilograms per meter, resulting in individual drum weights of 20 tons. A total of 54 drums were produced and tested at the Nexans factory to ensure compliance with stringent quality standards. Testing included assessments for partial discharge at 330 kV, 1 minute, and high voltage endurance at 440 kV AC, 60 minutes, ensuring the cables met operational reliability requirements. Transportation and handling. Specialized logistics were employed for cable transportation from Korteilud to Tierfed. Given the significant weight of the cable drums, a specially designed drum carriage was used to handle and transship the equipment efficiently. The drums were quickly loaded onto funicular platforms, enabling smooth transportation along the 3.6-kilometer tunnel to the installation site. Cable laying and installation. The cable laying process began with precise positioning using standard clamps, each measuring 600 millimeters in length and secured with 12 bolts. These clamps were spaced strategically to ensure stability and minimize mechanical stress between adjacent clamps. The 24% incline of the installation route necessitated precise engineering and careful execution to maintain alignment and structural integrity. Jointing works. The project involved the installation of 48 cross-bonding joints, rated for 400 kilovolts, which were equipped with integrated partial discharge sensors. These sensors allowed for continuous online monitoring, ensuring long-term operational reliability. Each joint was meticulously installed and inspected to align with the high-performance standards of the cable system. Final testing. Upon completion of the installation in April, the system underwent final testing to validate its performance. The tests included a high-voltage endurance check at 400 kilovolts AC for 15 minutes and a partial discharge evaluation at 330 kilovolts, confirming the installation's readiness for operational use. Outcome. The Axpo Project Linthal exemplifies engineering excellence in overcoming the complexities of installing high-voltage underground cables in challenging terrains. The successful execution of this project ensured the seamless integration of the pump storage plant with Switzerland's power grid, contributing to the country's energy infrastructure modernization. Forging and pressing technologies are cornerstone processes in heavy industry, enabling the production of high-strength components critical for demanding applications. By shaping metals under immense pressure, these technologies create parts with superior mechanical properties, making them indispensable in industries such as aerospace, automotive, construction, energy, and shipbuilding. Key figures in forging and pressing. Production volume and scale. Globally, the forging industry produces over 20 million metric tons of forged parts annually, with growth driven by demand for lightweight, durable materials. For example, in the automotive sector alone, forged parts contribute to nearly 50% of the vehicle weight, including components like crankshafts, gears, and connecting rods. Pressing capacities. Modern forging presses can exert forces up to 80,000 tons, enabling the shaping of massive components such as turbine shafts, railway wheels, and aerospace landing gear. Hydraulic presses, which dominate the heavy industry landscape, typically operate in the range of 1,000 to 50,000 tons, providing the flexibility to forge both intricate and large-scale parts. Environmental and economic impacts. The adoption of advanced forging and pressing technologies has significantly improved energy efficiency and reduced waste in heavy industry. For instance, isothermal forging processes, which maintain consistent temperatures, can reduce energy consumption by 20 to 30% compared to traditional forging. Furthermore, integrating automation and robotics in forging lines has increased productivity by up to 50%, minimizing human error and reducing production costs. The aerospace industry, for instance, relies on open die forging to produce critical parts like jet engine shafts and structural components with exceptional strength and fatigue resistance. Closed die forging. Closed die forging, often referred to as impression die forging, allows for the mass production of complex components with tight tolerances. Forging technology in heavy industry. Open die forging. This process is essential for creating large components such as shafts, cylinders, and rings, often weighing over 100 tons. In heavy industry, this method is used to manufacture parts such as turbine blades and high-pressure valves. Its efficiency is demonstrated by its ability to reduce material waste by 20 to 40% compared to machining processes. Pressing technology in heavy industry. Hydraulic presses. Hydraulic presses are integral to forming operations, such as sheet metal forming and deep drying, used extensively in shipbuilding and automotive manufacturing. These presses provide precise control over pressure and speed, making them ideal for producing large components with consistent quality. Mechanical presses. Mechanical presses are known for their high-speed operation and are typically employed in applications requiring repetitive, high-volume production. In the construction industry, for example, mechanical presses produce rebar couplers and structural components at rates exceeding 200 strokes per minute. Big bearings in windmills are crucial components that support the rotating parts of a wind turbine, primarily the nacelle and rotor shaft. The main bearing, typically a large slewing ring or pitch bearing, ensures smooth movement and stability under heavy loads and high stresses. It allows the rotor blades to adjust their pitch for optimal wind capture. In addition, the main shaft bearing supports the rotor hub and connects it to the drivetrain, transmitting rotational energy. These bearings are engineered for durability and performance, enduring harsh environmental conditions, extreme loads, and continuous movement to ensure efficient energy production. The motor rebuild industry has gained significant traction in recent years as companies and individuals seek cost-effective and sustainable solutions for maintaining and restoring electric and internal combustion motors. With a global focus on sustainability, rebuilding motors has emerged as a practical alternative to purchasing new equipment, helping industries reduce costs and environmental footprints. Market overview and growth. The global motor repair and rebuild market was valued at approximately $34 billion in 2022 and is projected to reach $45 billion by 2030, growing at a CAGR of around 3.5%. This growth is fueled by increasing industrialization, the need for efficient energy use, and the rising adoption of electric motors in various sectors such as manufacturing, automotive, and energy production. North America holds a significant share of the motor rebuild market, accounting for 30% of the global revenue in 2022, followed closely by Europe and Asia Pacific. The latter is expected to grow at a faster pace due to rapid industrialization in countries like China and India, where demand for rebuilt motors in manufacturing and transportation is particularly strong. Industry segmentation. The motor rebuild industry caters to various motor types and sectors. Motor types. AC motors. These constitute the largest share, representing 60% of rebuild projects, as they are widely used in industrial machinery and HVAC systems. DC motors. These are commonly used in electric vehicles and specialized industrial applications, accounting for 30% of the rebuild market. Specialty motors. High-efficiency motors used in robotics and aerospace represent the remaining 10%. Key sectors. Manufacturing. Over 40% of motor rebuilds are commissioned by manufacturers to ensure the longevity and efficiency of production lines. Automotive. As electric vehicle adoption surges, rebuilding electric motors accounts for 25% of industry activity. Energy. Motors used in renewable energy applications, such as wind turbines, represent 15% of rebuilds. Others. HVAC, mining, and marine applications constitute the rest. Cost savings and environmental impact. A rebuilt motor typically costs 40 to 60% less than a new one. For example, rebuilding a 200 horsepower motor may cost $8,000 to $10,000, compared to a new motor costing around $15,000 to $18,000. Over time, organizations that invest in motor rebuilds can save thousands of dollars while maintaining optimal operational efficiency. Rebuilding motors also reduces waste. Annually, the industry helps divert over 1.8 million tons of motor-related waste from landfills. Additionally, using refurbished motors lowers the demand for raw materials like copper, steel, and aluminum, which are resource-intensive to produce. Challenges and opportunities. The motor rebuild industry faces challenges such as the increasing complexity of modern motors and the shortage of skilled technicians. However, these challenges present opportunities for technological advancements and workforce training. Emerging technologies like predictive maintenance and AI-powered diagnostics are transforming the rebuild process, reducing downtime, and ensuring higher quality results. The production of the ITER vacuum vessel sector involves a multi-step, highly detailed manufacturing process, ensuring the integrity and functionality of the vessel in the ITER tokamak. The process begins with the inboard segment, PS1, where the inner shell is formed, and crucial features such as FSH hole machining and E-beam welding are performed. The outer shell is welded together with precision, followed by upper segment fabrication, PS2, involving extensive machining and rib welding. The lower segment, PS4, includes E-beam welding, shell machining, and installation of key components like the TRS and ribs. Once the individual segments are prepared, they are assembled, with each segment being meticulously fit and welded together. During this process, the inboard and upper segments are installed, with splice plates fitted before the assembly is moved to the fat shop for a helium leak test. The equatorial segment, PS3, focuses on the inner shell, FSH modeling, welding, and rib installations before moving to the final machining stage. The completed vacuum vessel will house the plasma within the tokamak's donut-shaped chamber, providing a high vacuum environment necessary for plasma containment and stability. Hyundai Heavy Industries is responsible for the fabrication of these sectors, with Europe and Korea sharing the procurement responsibilities. The vessel's design consists of several segments, including the inboard, upper, equatorial, and lower segments, each with specific production phases. It will feature 44 access ports and modular components, including in-wall shielding blocks, thermal shielding, and actively cooled blanket modules, contributing to radiation protection and cooling during fusion reactions. The vessel's dimensions, weighing up to 8,500 tons, make it a crucial part of the ITER project's experimental fusion research. The Natec Cable X copper wire stripper is designed for efficient wire processing, removing insulation from copper cables. It uses rotating blades to grip and strip the insulation, exposing the copper core. The machine operates by feeding the cable through an adjustable set of blades, which cut through the insulation without damaging the copper wire. It accommodates various cable sizes, providing flexibility for different applications. The stripped copper is then collected for recycling or further processing, offering a fast, reliable solution for wire recycling and reducing manual labor in the process. The production process of super radiator coils begins with a close collaboration between design engineers and clients to fully understand the specific heat transfer requirements and material needs. Engineers assess the application's constraints, materials, and installation details to create a custom design or modify an existing one. After designing, a prototype is constructed and tested in the company's advanced lab, which includes a state-of-the-art wind tunnel. This tunnel, unique in its ability to vary refrigerants, verifies the performance of the coil. Once the design meets rigorous quality standards, manufacturing begins at one of Super Radiator's 4 facilities. Tubes, fins, and headers are crafted from high-quality metals selected for durability and heat transfer efficiency. Precision welding and brazing techniques ensure strong, leak-free joints. After assembly, each coil undergoes thorough testing to confirm its reliability and performance. The final products are delivered to clients, often offering solutions for specialized applications, including HVAC systems and oil coolers, across diverse industries. The manufacturing process of large-size roller bearings, such as the spherical roller bearing, involves several key steps to ensure precise performance and durability. The process begins with forging, where raw materials are shaped into basic forms under high pressure. This is followed by turning, which refines the forged material into a cylindrical shape, ensuring dimensional accuracy. Next, cage drilling is performed to create spaces for the rollers inside the bearing, followed by roller cutting to form the rollers to the required size and shape. The rollers undergo heat treatment to enhance their hardness and strength, ensuring they can withstand the high loads they will bear. Similarly, the bearing rings are also subjected to heat treatment to achieve the desired properties. Once heat treatment is complete, the components are ground to achieve smooth surfaces and precise dimensions. Quality control ensures that all components meet the required specifications through detailed inspections and testing. Finally, the bearing is mounted onto its intended application, ensuring it performs efficiently under operational conditions. The final steps include assembly, where the rollers, cages, and rings are carefully assembled, and packing, which involves securing the bearing for transportation. The Roll Neck Milling Machine WZF from Rottler Maschinenbau is a specialized machine designed for processing rolling mill rolls. It accommodates workpieces up to 10,000 millimeters in length, with a machining length of up to 1,000 millimeters. The machine features simultaneous processing using 2 spindle heads, enabling efficient machining. Additionally, it supports end-face processing of the rolls. Equipped with the Synchronous 840 DSL-CNC control, the WZF ensures precise, automated operations, delivering high productivity and excellent results for large-scale roll manufacturing applications. The Win GD14RT Flex 96C, formerly known as Wärtsilä, is the world's most powerful diesel engine. This 14-cylinder low-speed engine powering a massive 400-meter-long container ship. With an output of 80,080 kilowatts, 108,920 bhp, at 102 revolutions per minute, it is the largest and most efficient engine for ship propulsion. The 14-cylinder RT Flex 96C represents a significant advancement in marine engineering, combining the reliability of proven engine designs with the flexibility of RT Flex common rail technology, enabling it to meet the power demands of the latest generation of large container vessels.